Hi everyone, my name is Suman Karumuri. My pronouns are he, him, and his. Today I'm going to talk about SlackTrace, a new tracing tool we have built at Slack. So just something about the name is like there's a talk deadline. The project doesn't have an internal name, so we just picked that because that was the top of my mind at that time. So it's not how we trace Slack, but it's the name is there just for the sake of the talk. So just a little bit about me. So I'm a senior staff engineer at Slack, and I work on the monitoring team there. I lead the team. I love building and running petabyte scale observability systems. And at Twitter, so I used to work at Twitter, Pinterest, Facebook, like that strip there. And I ran Elk at a lot of these companies, and we also replaced Elk at Twitter with a system called Loglins, which is a log search platform which manages about 2 petabytes of data today. I was a tech lead for Zipkin project at Twitter, and I was also on the Open Tracing Advisory Committee, Customer Advisory Committee, something. And I also built end-to-end tracing at Pinterest. The system is called Pintrace. On the metrics front, I was part of like Twitter's metrics stack. We ran OpenTSDB at Pinterest. We run at Slack. We run like one of the largest Prometheus clusters in the world. I also wrote an in-memory metrics storage engine called UV for OpenTSDB. In general, I'm actually very interested in distributed systems, cloud infrastructure, and infrastructure in general, systems. So I'd like to start with a really, really quick overview of tracing. Going back, it is slow is the hardest problem to debug in a distributed system. So tracing was built to identify where the bottlenecks are in the system, right? Everybody builds their own version of tracing. So, that gave rise to Rodrigo's 10th rule of distributed system monitoring. Any sufficiently complicated distributed system contains an ad hoc, informally specified siloed implementation of causal tracing, right? So then we have these tracing systems today where it's a bit more formalized view of capturing this information in a trace and then analyzing it using cool visualizations and analytics tools. So what we did to trace this data is we took a request-centric view where we follow a request along its execution paths of all its microservices, and then along its request execution path, we capture the spans, which is the trace data. We collect this data, store it in some data store somewhere, and then generally, these systems have a find traces view where you search for the representative traces, and then you look at one of those traces in a trace view, and sometimes you also look at this data in a service graph, right? This is generally a very high-level view of tracing systems, right? Some tools and vendors do provide analytics on top of this trace data, right? So having built these systems, right, like at Twitter, Pinterest, and like Slack, one of the things that there's an emerging theme is like these systems are very complex. Like all those like Death Star diagrams you see like in slides are real, and honestly, those diagrams actually are not very useful in practice at all. It's like just a cool visualization of how complex everything is. What we found from these traces, like using these traces at scale, is there are like a lot of problems. You need a lot of intuition and expertise to understand, to find representative traces. So once you're tracing these systems, unless you know more or less what you're looking for and search for the right thing, it's really hard, the data you collect won't be useful unless you have to have some sense of what you're knowing. And even if you find the representative trace and like you are looking at it in a trace view, the tools stop there. They don't tell you what's slow. Like it's left as an exercise to the reader what is slow or why it is slow, right? So as a result, tracing tools have a very steep learning curve. The normal pattern is like a handful of people at a company get really good at it, and then they use it to derive most of the insights. But for a wide swath of employees, tracing is not generally is not the tool they reach out to ask and answer questions about their system's performance. So service graphs are cool, but outside of like demos in like real production scenarios, they are not very useful. At least like in my experience. And traces cannot be used for triage. So if you have an ongoing production issue, generally traces are not used for triage. They're generally used to identify bottlenecks and like identify bottlenecks and fix point issues, performance issues. But when you have an ongoing incident, traces are generally not the tool you would reach out for. They can help if you know that, hey, like trace would answer this question, but generally they may not be, right? And there are other problems with traces, like you sample at scale, you have instrumentation overhead, and as a result, what happens is when you're capturing less data. As a result, the number of questions you can ask of your traces generally diminishes at scale. So what happens is once generally tracing systems are built, they are deployed, you get some quick wins, which are very interesting, and then tracing usually falls on the wayside. It becomes a nice-to-have tool as opposed to a must-have tool, right? Like if it goes away, like if your prom goes away, all hell breaks loose. If tracing goes away, right? So, but the thing is, traces have very rich and complex data in them. The problem we have found by building these systems is the data in the traces is exposed as literally two views, like a trace view and a service graph view. It's basically like taking all your fancy Prometheus metrics or logs and everything and just providing a single dashboard to your data, right? That's a single view into your data, and it's pretty constraining because you can't ask any more questions of the data. It's like you have these views and then that's pretty much it, right? It's a waste of the data we collect. So that's why we want to make trace data more useful. And to make it more useful, we want to make it more accessible, right? That's our goal. So the image there basically shows like initially there's a lot of hype and then there are deflated exceptions, and generally that's where it's stuck, right? So what do we want to do? We want to access this traces as raw data, right? So why do we care, right? So as I said, we only get fixed views into the data. But what if we can access raw data? If you access raw data, you can slice and dice these spans across various dimensions to get unique insights, right? For example, we can mix and match the data from different spans to ask and answer different sets of questions that we couldn't ask before, right? We can build custom dashboards and analytics, all the things we do on logs and metrics today, on traces as well, right? To get the value out of them, right? So we were thinking about this, and I came across a strange like revelation, right? For me, it was, hey, we access metrics and logs as raw data, right? Why not traces? Traces, you don't even know what the data format is. You just go to Zipkin UI or Jaeger UI or your tool, and then you just put in some information, and then it spits out a view. That's pretty much it. You don't access raw data in traces. Why is that? So having thought through this, and we have identified a few issues, and like we got a few insights, right? So if you look at like tracing today, you have these open tracing APIs where the trace, that's how you instrument your applications, right? Open tracing is a complex but clean API, right? To instrument your application for tracing, right? And on the other end, you have cool, clean, intuitive UIs, which is you have your trace view and your service graph, right, to look at this data. But what's in between is pretty much undefined. It's implementation defined. It's very complex, right? The span formats are very complex. And they are designed to fit the needs of the tools, the questions they answer, the diverse storage systems they use, the diverse query languages they use. All the internal formats are designed to fit into this this diverse model of spans, right? So what is complex about this span formats, right? So we looked at all the span formats, or at least like the publicly available ones, and here is what we found, right? The reason span formats are complex is they are very network-centric. Like distributed tracing started from a very network-centric perspective. So the span formats are very network-centric. And as time went on, people added UI, things that are needed for the UIs or the tools into the spans, right? So the span formats organically grow. And there are like interesting side effects of this, right? So if you look at a span format for Zipkin, Jaeger, any of these projects, one of the things you would see is, for example, if you look at a span which represents how much time something happened, and then you have two ways to represent the sub time, right? One way is you can use your child spans to represent sub parts of that span. And you can also technically use annotations. And people do that, right? So there are two ways. And then there are some UI-driven aspects to these spans. For example, Zipkin has annotations and binary annotations. What's the difference? Annotations are sub-events in a span that you would look at that are shown in the UI, whereas binary annotations are the same things, but they're not shown in the UI because they're supposed to have binary data, right? And there are like logs and tags in these spans. What are logs? Like this is like something from a storage concern, right? Like if you have application logs, you don't want, like generally these systems are stored in like Cassandra or something, and you don't want to index this data in a specific way. So you have logs, you put that data in logs, and then you put different data in tags, which is like a more columnar friendly, analytics friendly thing, right? And then there are network-centric concerns, right? So Zipkin has single host, like multi-host spans, where span events can belong to multiple hosts. Zipkin, Jaeger has a single host span, where every span can only be produced, contains the data produced from a single host, right? There are wire send, wire receive annotations. And then there are complexities around span relationships. And there are just basically too many span formats out there, right? Each with its own like take on what a span should contain. And most of these are driven by what the tools need, right? So, and then there are other influences, like we talked about, like the data model of these spans is influenced by the storage systems we use, the query model exposed by those systems, and the latency of those queries. All of these impact the span format today, right? So, and this also has impact on how much the cost of the tracing infra and which query languages we use. So what we do is to address these complexities, we built a very simple span format, which is pretty minimalistic, called a span event, right? What is a span event? A span event is a very simple format for representing a span, right? So a span event, here are the goals of this the span event we designed. Span event, we want it to support querying raw data using SQL. We want these spans to be easy to produce, right? We want this a span event format. We don't care if these spans are part of a trace or not, right? And a span event should be but we want to capture the full fidelity of the spans. If you take a Zipkin span, Jaeger span, or an open tracing span, or open sensor span, we want to capture all that data in our span. So we want to capture that full fidelity. We just don't want to lose that data, right? So a new event has the following fields. Like we have an ID, which is the unique ID for an event. We also have a timestamp, which is the time at which the event started, the duration, which is the time it took to run this event. We have something called a parent ID, but which establishes a relationship between two spans. We call it parent ID, but it establishes a relationship. It does not have to be a parent-child relationship. We also have a trace ID, which is an ID that we use for deeply nested spans. Every event has a name. Every event has a type, which could be a service name. We also have tags, which are arbitrary set of key value pairs for all these events, right? And we additionally have a new field called a span type, which is similar to a kind. And then it shows the type of span, whether it's an annotation, whether it's a client span, server span, anything like that. So the reason we did this is it actually looks very similar to the existing span formats out there, but it is very minimalistic, right? So we have these variants on these spans. Like the reason span formats are very complex is they have these additional ideas that are tagged onto them over time, right? So like annotations, and annotations are these point events that are part of a span. So we just make it a span type, And then it is also a span event, but we just declare that as an additional child span that the UI wants to do something about, as opposed to like some nested structure in a current span, right? We have point spans, which are spans that happen for an instant. So these are spans with duration of 1. We also have one-off spans, which are spans that are not related to a request at all. It's just something that happened in the system, right? We picked SQL as the query layer for these data because SQL is widely used and popular. It is simple to get started with this data. And the other advantage is SQL is verbose, but yet very expressive, and we can do all sorts of complex joins on this data, right? And the more important reason we chose SQL is it's supported by a wide variety of storage backends that are available out there, right? So we took all of these ideas, put them in a project that is internally called feed tracing, and then the goal of this project was we want to represent our traces as causal span events that can be queried over SQL, right? So this is the part where like I'll talk about like our pipeline and infrastructure, but these bits are not very exciting, but it's like pretty standard. We have our apps which generate spans, right? We generate span events, some internal apps. And then the span events that are generated by apps are written to Muron, which is Slack's internal reliability event pipeline. It's an open source analogy of that would be Scribe-ish. And then we also have a HTTP endpoint for ingesting these span events called Wallace. The Wallace service takes these span events, writes them to Muron. And then we also have trace adapters. So the thing is, because we invented a new span format, we don't want to invent new instrumentation into the applications. We just want to use this open source instrumentation that is already applicable, and we already have frameworks and applications that have instrumented them. So we wrote adapters for Jaeger spans and Zipkin spans. So applications can just point their endpoints to these spans, and then we can get these things. And then Muron takes these spans, writes them to Kafka, and then we have several Muron consumers that send the data to Honeycomb, our internal data warehouse, which is a Presto cluster, and we have an internal fork of Zipkin to handle this data, and we send it to that too. So these are just like some views. This is a view of a request when you send a message in Slack. So the API is called chat.postMessage. We send the request, and this is a trace view of that. We trace memcache calls, database calls, gRPC, HTTP, and all those calls. So this is like just part of that request. We can build heat maps and dashboards on this data, both within Honeycomb and also within our internal data warehouse. And we can also access this data in our data warehouse using complex SQL queries. Here is an example of a UI with a sample query that shows, show me all the traces today that have an API method and that came from a specific host. So it's like a cross-span join query, right? So that's like that's basically to prove that, hey, we have the system, it works, right? So today we run the system in production, we trace 100% of our requests in dev and about 1 to 2% of our all API requests in prod, right? So as expected, this tool has provided visibility into what is happening. That was the most important question for us. In addition, tracing has helped us, as expected, to identify the performance bottlenecks on our system. But more importantly, it helped us prioritize which bottlenecks to fix. Because previously, if you use a tracing system, it will tell you something is slow. But because you can't access the trace data, you don't know how prevalent it is or whether it's affecting your largest customers or your smallest customers, right? So with the trace data, we were able to do that. And the most surprising bit for me is by allowing our users to open up the trace data and access it in any way. The most interesting thing for me is we were asking questions of this data without adding additional instrumentation. Generally, whenever you have some question about how something works, you have to go in and add some additional instrumentation, add a counter, metric, whatever, to get the insight. But with trace data, we didn't have to do that. Most of the time, almost every single time there is a production issue or anything, we could go into the system and just formulate a new query on this data and get an answer without adding additional data. That was very powerful. Some teams today do use traces at Slack as a result for triaging production issues. So we had like a major incident where like our GitHub was down, internal instance of GitHub was down, and we weren't sure why, because we made a massive change to some of the components that the pipeline depends on, and we actually used traces heavily to triage that issue and identify like bad hosts and like take them down very quickly. And the most interesting bit for us is how we use the trace data. I'll give you 3 examples. Well, I only have 2 on the slides, but I'll give you 3. So the first one is, as I said before, we use memcache. We use caching heavily in an architecture. One of the things is caching does not have the same effect for all the customers, right? So we have memcache, for example, for large customers, there can be hundreds of memcache calls in a single request, right? For small customers, there'll be tens. So the perception of latency from memcache for a given customer is dependent on a specific endpoint and their use case. So what we were able to do is we were able to ask very pointed questions that you couldn't ask off of your data before, which is, hey, does memcache contribute to P99 latencies for this large customer, right? So for example, if we want to make our performance better for our largest customers, how much should I invest in memcache, right? Is memcache the right place to invest? Our trace data told us that yes, it is, because what we found is from the trace data is, hey, our largest customers always hit P99 latencies, so we cannot just look at 99. We need to probably look at 3 nines and optimize that, and that's one insight we got out of it, right? And then the other thing we found interesting answers to is we have these API calls for IDR. So Slack provides this feature called international data residency, where your data is actually spread across, for legal reasons, some customers want their data in a specific geographic region. So when we launched this feature, generally when you launch features like this where you keep the data in a different geographic region and it's in a different AWS data center, any slowness is generally attributed to this like cross region calls, right? We really don't have data from metrics and logs to really prove one way or the other whether it is the case or not. But with traces, we could prove whether how slow the IDR calls were making the actual endpoint calls. For example, if the IDR calls adds 100 milliseconds of latency, right, a cross-region call, if the overall call takes 4 seconds, that 100 milliseconds is not optimizing that 100 milliseconds or blaming it is not going to help, right? So it has helped us compare in-region queries with cross-region queries to know whether the additional latency we are seeing for IDR customers is because we are making that network hop across the region or not. Similarly, for our EKM customers, which is like basically encrypted Slack messages, we can also say whether the latency for API request is coming from our slow customers. The third bit where we use traces very heavily is, one of the biggest problems with tracing is you have to like trace your requests across the stack, right? But our Slack desktop client uses WebSockets. If you do a network console, you would see it. So we use WebSockets, so we maintain a persistent connection with some edge network. And one of the interesting things is traces are not very well suited for tracking a request through those through WebSockets. And so what we did was we modeled the WebSocket state as a trace in itself, and we have a client trace and a server trace, right? And what we did with this is now, because it's SQL, we could ask, hey, this request is, this customer is experiencing slowness. Is it because he's in degraded mode, right? Because degraded mode is a state of the WebSocket, and if the WebSocket network is down, we go to the backend. But because we have a client state and we have this degraded mode, we can mix and match independent requests, right? Like the state of WebSocket is not even a trace. It's not part of any request. But yet, we could take this data, mix it with our trace data in a SQL query and ask, is this slow because the customer is running integrated mode or not, right? So we were able to get some unique insights which were not possible if we couldn't access this trace data as raw data before. And in future, we want to build canonical instrumentation based on trace data. As I said, like we were able to ask a lot of questions about the trace data that we couldn't ask before. So what we want to do going forward at Slack is we want to make the trace data as the default canonical instrumentation. So when we launch a new feature without adding any additional instrumentation, we want the trace data to answer basic questions about the health and performance of our application. And we are also going towards end-to-end tracing, where we want to start, where we are starting to trace the client. We start the trace on your client. So when you send a message, we trace it all the way to the database call. I had a demo planned, but because of the spotty network, I didn't like show it. We also add an auto analytics tag on our span, where in the data warehouse, if a span has that, we automatically generate custom analytics for users without users having to do anything other than just say that this span has this tag, right? In future, we want to open source the system, and using this system, we want to bridge the gap between events, logs, and traces. We also want to, at some point, investigate like a more concise query language for querying this data, because right now, SQL is honestly verbose if you have a lot of nested calls. And to summarize, I believe that querying trace data as raw data is extremely powerful. It'll unlock a lot more use cases from your trace data, and it'll be extremely valuable, I think. And the span event is actually a simplified span format that we designed to allow querying traces as raw data. SQL is a powerful tool to query these spans. And we have put all of these ideas together in feed tracing or SlackTrace, and it works well. Previously, if I built a tracing system, I had to knock on every team's door and say, hey, like, please use tracing. It'll be very useful. Now, people knock on my door, so I consider that a success. And ask. So this is the team that helped me support and build our team. So thank you for giving me this opportunity. And yeah, we are hiring. So if anybody wants to join, thank you.
Round of applause. We've got time for a couple questions, but first is Mania Abdi here? Right there. Okay, great. We're going to get you set up in the back with audio. You see him waving his hand over there? Great, thanks. Okay, questions. Questions right there.
Hi. One of my question is, what kind of data were you storing in data warehouse? Is it the raw spans, or do you have your own format?
So I showed you a span event format, right?
Yeah.
The data in Honeycomb and the data in data warehouse is exactly the same.
Okay.
Yeah, there is no difference.
So my other question is, you're trying to replicate the data in Honeycomb as well as your data warehouse. Don't you see it as additional cost?
It is, but for data warehouse is Presto, so it's mostly the data is stored on S3. And we only query it on demand, so the storage costs are low. We get infinite retention because of our data warehouse. Whereas the data in Honeycomb is only for like a couple of weeks at this point, and it's used for so the way we think about Honeycomb versus data warehouse is Honeycomb for recent data, short interactive queries, data warehouse for complex analytics over long time ranges of data.
Okay, and I also see that you have used Zipkin.
Yeah.
So what is the backend that you have used along with Zipkin?
ES. Elasticsearch.
Elasticsearch?
Yeah.
Okay, maybe I can sync up with you later.
Sure, yeah.
Great. Next up.
I guess one question is, because you're doing a lot of analysis on the data, right? And I noticed you're doing 1% to 2% sampling, right, of your trace data, right? I guess the question is how can you tell the data is statistically robust, right? Since you're only collecting 1 or 2% of the data.
Yeah, great question. So what we actually do is, the way we do sampling is different. So we have a 1% base sampling rate, which is the sampling rate that always happens, right? The additional 1% is actually our CE person or some team turns on tracing for a specific team or for a specific customer or a specific request. So as a result, from the 1% sampling, we get like a general idea of how things are going or what kind of things our systems are doing. And from the additional 1%, we get the specific data. So the beauty of ours is like this tiered sampling is generally tracing is like sampled and then you don't get a specific request. So with our sampling scenario, we handle both specifics as well as generic requests. So to answer your question, the specifics help if it's a specific problem, and the base sampling helps with general things like, hey, how does a chat message get processed for a large customer? Yeah, one request from like a day is good enough.
All right. One more question over here. And actually, while we take that question, if we could maybe get you set up.
Okay.
Sweet. So you can keep that mic on. Got it? Nice to meet you. Okay. Just get set up over here. Okay. Yeah, big round of applause. That was a great talk. Really appreciate it. But don't go too far because we got a question here.
Okay, yeah, really interesting talk. I just have a question. So you talked about 1% sampling, but now you have these interesting SQL queries that you can use. Have you thought, or are you thinking about perhaps making some of these queries that become interesting, like standing queries on more than 1%, such that the traces that are filtered by the queries get stored somewhere?
Yeah, we can actually filter our traces to say that, hey, like, tell me all the SQL queries that are actually this query, and then we can actually filter our traces by that.
But this is currently on the 1% that you already stored, right?
Yeah, if it's a general query, we can do that. But if it's a specific query, we trace those specific requests. So generally, we turn on tracing when we launch a new feature along new paths or something. Yeah. So that's our use case for those specific queries generally.
Right.
Yeah.
Okay. Thanks.
Great. Quick question? Yeah, you got a quick one? Where's this coming from? Yeah, why not? Why not?
All right, thanks. Suman, so if you're just taking 1%, if you have a long tail distribution, you're not going to really get a sense of what the application latency distribution is.
So yes, we don't. But we have metrics and we have metrics for that. So if you need precision, we go to metrics. And that is actually more efficient from a instrumentation perspective, from a storage perspective, and a cost perspective.
But would you be able to get the correlation that you did if you're only taking 1%, the one you just mentioned?
So generally, 1% works out very well.
Okay.
Yeah, I mean, at scale, of course, over a period of time.
Okay.
Yeah.
This sounds like a birds of a feather session in the making. Sampling when and how to do it and why. Okay. Thank you. We're all good. Okay, another round of applause. That was excellent.